Currently, millions of amputees around the world rely on body-powered or myoelectric prosthetics. These traditional methods take months to learn, do not provide a natural and intuitive control, and tend to cause comfort and skin irritation issues.
This is where non-invasive brain-computer interfaces, or BCI, which is the focus of our capstone project, comes in. Non-invasive BCIs can use techniques such as EEG to measure the neural activities and decode it into control commands for a prosthetic limb. It enables direct communication to provide a more natural and intuitive control for the user.
There are three core components to our project. The first is signal acquisition, which is comprised of the headset and electronics that convert the brain biopotentials into digital signals. Second is the software stack, for processing and translating the signals into control commands for the prosthetic. This includes a signal processing layer for feature extraction and a deep learning model for decoding the data. And lastly is the device output, which in our case is a virtual model representing a prosthetic hand.
So far, we have completed the design and fabrication of the electronics, along with the first iteration of the headset. Several iterations of the PCB design had been made. These involved several changes to our chip selections, along with routing issues, as the PCB is a mixed signal board and required separation of AC and DC signals to reduce interference and our highly sensitive signals. We're still waiting on some components due to a global supply shortage of ICs. However, progress is moving swiftly.
For our software stack, the code base for the signal processing layer is being developed, while the deep learning model is currently being trained and fine-tuned on open source datasets. We have simulated real-time data and are working on a performant way of extracting useful features through various digital signal processing techniques. We've also been trying out different hybrid deep learning model architectures due to the performance uplift compared to single model architectures and been optimizing their hyperparameters.
Due to the complexity of this project, we are slightly behind schedule relative to our initial proposed timeline, and more complications will likely arise in the future. This means that we may need to sacrifice some performance to complete it within the short 7-month timeframe.
With the remaining 4 months, our next steps involve finishing the hardware side, collecting our own dataset, extracting the most useful features, and fine-tuning our deep learning model. Then our final step will be to integrate the model's decoder commands with our virtual prosthetic hand to demonstrate our model's efficacy. My name is Oliver.
And my name is Jody.
We're super excited about what the future of prosthetic control technology will bring.
And you can thank us later when we've revolutionized prosthetic control with our project.
Thank you for listening to our project progress update video.